So let's look at this exact text recognition. So some images, some digits in front of us. And I think for us, it's very easy to understand. This is 3, this is 5, this is 0, this is 0, this is 2. We can do it. But if you start to think, how do you program? How do you write a code that actually takes this as an input and tells you this is a 1, this is a 3, this is a 9? You don't know. There are no laws. What are the laws that we are going to formulate for that? It's very difficult. Is there a code book that we can say, okay, given this code book, if I see this image, it has to be a 5. Now this 5 is very different from the way this 5 is written. It's quite different from this way. It's oriented. This is again oriented quite differently from all these other 5 images. So what is the rule book? What are the laws or equations that you are going to formulate that takes these diverse images and they tell you this is a 5, this is a 9, this is a 3. It's very difficult. So what we as humans are doing so easily, when we start to approach things, it's very, very difficult. And one thing, and I don't know, like at least when I think whenever I'm trying to program, I have an equation in mind. So that's the thing. So if I have an equation in mind, I can program. If I don't have an equation in mind, I have to come up with some equation and then I have to code. In this case, I don't even know what are the equations that I should come up with. So we don't have an answer. So we don't have analytical solutions available. We don't have this one, or a quadratic function, or a polynomial function, or an exponential family function. We don't have that. So it's very, very difficult. So what we have to do, we have to resort to non-analytical solutions. So the learning has to be done through data. I can't specify a list of rules that this is what is acceptable, this is what is rejected. There is no code book. All it has to do is on its own. The machine has to learn this unknown function f on its own without any rule book, without any code book from this given data. So we are looking, so again, machine learning, we are trying to solve for this unknown f using non-analytical methods. That's what we are trying. Okay, so here's a very interesting flow chart. So we have some available data, and it's basically data of this sort, which we have examples and outcomes. And from this data, I'm learning this unknown function f. It's a very complicated, complex function, but let's suppose we are learning. And once we learn from this data, the output is a model. The f. That unknown function can have any data set that was never seen before. I pass this data set through this model, and it tells me this is the outcome associated with this novel data. So this word learning is basically inference we have here. And because it's inference, so that's why you have statistics also, because you want some probabilistic estimates, you want some statistical inference on the outcomes that you are generating from that. So again, so on the vertical flow chart, we are learning that unknown function f. And that unknown function f, there is no analytical form, it is a non-analytical solution. We are going to highlight it more in deep learning. And the horizontal workflow thing but inference, that's all. So that's the whole game. We have available data, we learn the function, we have a model with us. Whenever a new data comes, I actually predict what my model tells me about that data. So that's what we have. So learning versus inference. So there's some nomenclature that we are going to adopt. So we have available data, and that's what we are going to call as training data. And novel data I'm going to call as testing data. And these two data sets are disjoint, meaning that during learning, the testing data is not seen by the model at all. I don't want my model to have access to novel data. That's cheating. So I want my model to be good enough to respond to unseen data, to respond to novel outcomes, so that we can say it has a good prediction power. So that's very important. So there are some challenges that we are associated with it. So it's simple. So we said, okay, we have a machine, and let's say that machine can learn. We can give them a lot of data, and it outputs me a model. But that model doesn't always give me a good inference. And there are some reasons for that. And the first challenge is basically a structural challenge. The structural challenge is the following: that the training data set is usually quite different from a testing data set. So a machine has only extracted features or learned information or knowledge from the data set it has seen. But what about the other features that are not present in the data? There is no way for a machine to learn. And we go back to very, very basic principles of conservation of law and mass and energy or information, and information can neither be created nor destroyed. You cannot create an information, a novel information from an existing information unless there is some hidden dependencies. It's not possible for a machine to automatically learn something new which it has not seen before, and probably that's the difference between human beings, that why we are the best of creation. That we are able to actually stick up some letters and we can construct new words on the fly without even having heard those words before. We're able to, like somebody pronounces a word and I'm able to tell you the spelling even though I have not heard that word before. That's real intelligence. And that's why some people actually associate artificial intelligence. That it's not intelligence that the machine is acquiring by itself. It is acquiring through this data, through this training data. So a lot of the time this training data and testing data are quite distinct. I want the model to be generalizable. Generalizable means that I've trained it on a particular training data set. It should perform as good on the testing data, on an unseen data, as it is performing on my training data. It should be generalizable to all sorts of data, particular to that problem. That's what I mean. So if it's chest x-rays, the chest x-rays coming from any hospital, from any x-rays, from any demographic, my machine should be intelligent enough to actually generalize to all these variations in the data set. So for that we need a training data to be unbiased. So although we have big data, but that big data is not unbiased. So that's another challenge. So how do you create an unbiased data set that actually generalizes to all the data set in the universe? It's a very, very difficult. I don't even know if there is a solution to that or not. So whether I'm actually using a training data or testing data, my performance will be consistent. If I'm getting a 90% performance today on some data set, I should get the same performance or roughly the same performance maybe 2 months from now, 3 months from now on another data set. I don't want my performance to be highly variable because then I cannot use that model. I don't know whether to trust that model or not. So these are some of the challenges that we actually encounter as far as generalization is concerned for machine learning. The third biggest nemesis is basically overfitting. Because what we try to do is that we have, let's say, millions of training data and we want to fit our model exactly to that training data. So I'm chasing a perfect training performance. That's what I'm trying to do. I want to have a model that exactly reconstructs the outcome for each training example. So I want for each training example, my model should give me the exact output. And if it is giving me the exact output, the training performance is 100%. But that may not lead to generalizability. And we are going to see one example right now. So if you are chasing a perfect training performance, you may compromise generalizability. And generalizability is far, far more important than training performance. So here is the trade-off. So we don't want our training performance to be so bad that there is no learning happening. But we don't want to chase it so much that we actually lose our generalization property. So that's a trade-off that we have to be very important. And the reason we can actually hurt ourselves from this first thing is because the training data is empty. There is noise, there is perturbations. There could be some non-physiological changes or disturbances or perturbations that I am actually fitting through the model, whereas my model should reject that because that is something that is contaminating my data. It's not adding any value or virtue to my data. So that is very, very important. So my training data has to be unbiased, which is not, and my training data should be pure, which again, it's not a truth. So training data has all these disturbances that we have. And sometimes it's quite impossible to differentiate. I can't differentiate whether something is noise or something is actually virtuous to us. It's very, very difficult. So these are the challenges that we have. So again, we have structural challenges, generalization, and overfitting. And these are three of the most profound challenges that are in machine learning. And because deep learning is a subset of machine learning, they eventually become the challenges for deep learning also. So all your deep learning methods are actually victimized by these three issues. So you need to have the structural challenge because your training and testing data is diverse. You need to generalize to unseen data. You want to have a consistent performance, and you don't want to chase. And you don't want to chase your perfect training performance at the cost of generalization. So that's very, very important. So let's look at this example that I actually made in MATLAB. So this is Fisher Iris data set. So this data set is basically talking about trying to understand different species of flowers. And the way it is trying to differentiate is basically using the width and length of sepals and petals. And here I'm just talking about the sepal length. So we have these two sets of points. So all these red points are basically setosa, and all these green points are versicolor. So that's what we have. So there are two species of plants, and just based on the sepal length and width, I want to differentiate which of these sepals belong to which species and which one belongs to the other species. So it's a binary classification problem. When I see this data set, I can very easily draw this hyperplane, this line that actually perfectly separates my red points from my green points. So I have a perfect separation, perfect classification between these two species. And this classifier, this linear classifier or a hyperplane in high dimension is good enough to answer any point. For now, if I look at this example. But what if we have some outliers? We have this green dot that is actually in the vicinity or in the neighborhood of the red cluster, and this red dot is in the vicinity of this green cluster. Now if I have this linear classifier, these 2 points will be misclassified. This green point will be assigned a red label, and this red point is going to be assigned a green label. So although my classifier is still linear, my performance has dropped, because here my performance was 100%, but here I have lost. There are 2 false positives. I have misclassified 2 points. But if I now change my performance, my training performance, I'm going to have this weird irregular surface as a classifier boundary. That's what we have. So here now I have made my classifier more and more complicated just to chase a perfect training performance. That's what we have done right now. But let's assume that these 2 data points were actually novel data points. The data set had never seen those data points. And actually this data point was a red species and this was a green species. But with this classifier, this originally red will be classified as green, and this originally green will be classified as red. So if I'm chasing my training performance to the core, I'm going to lose my generalizability. So that is very, very important. This is overfitting. This is the crux of overfitting. I can still be very happy with the linear classifier, although I have misclassified 2 points, that is perfectly fine. So I don't want to chase 100% training performance by compromising my prediction or inference on novel data points. That's very, very important. And we're going to see how do we actually attack this overfitting problem. Okay, any questions so far? See, we have some data issues. We have to generalize it to unseen data, and we have to fight this overfitting problem. That can very easily happen. All right. So there are different types of learnings. There are supervised learning, unsupervised learning, and reinforcement learning. And these learnings are usually used in 2 tasks. There could be more tasks, but usually we are going to talk about regression and classification, and as we go further, I'll talk about more. So let's talk about a supervised learning. So what is supervised learning doing? So you have a training data, again that vertical line, that's the learning line. You have a model, you learn the model based on this training data, and you have predicted outcomes. So this training data learns a model by coming up with a mapping between this outcome and training data. So now you already have a correct outcome. So let's say there's a model that I'm learning and I'm at the first iteration. I access this training data, my initial model guess predicts some outcome, but I already have gold standard ground truth for this data set. I compare, and based on this comparison, I revise my model. So this is what we call as supervised learning. So I have a completely annotated training data. Every training point has an outcome that is assigned to it. It's an expert outcome, it's a ground truth, it's a gold standard that we have. So all our data points are perfectly labeled. All our data points have all the available outcomes assigned to them by experts, and I can trust them with full confidence. So that's what we have. So in supervised learning, the way you are actually learning a model is guided by this completely annotated data. So you have inputs and all the correct labels or outputs to this input. If it is a classification problem, your outputs will be discrete labels. 0, 1, 1, 2, 3, 1, 2, 3, 4, 5, minus 1, 1. So these will be discrete labels. If it is regression, there will be continuous values. So that's what we have. So regression, outcomes are continuous values. Classification, outcomes are discrete labels. So that's a very, very simplistic discrimination between these 2 tasks that we have here. So that's what we have. So I have a fully annotated data set. I use my gold standard to update my model so that I refine the estimate of the model as good as possible so that it is a very good learning system, that I can use it on novel data set. That's what we have. So if I talk about the mathematics of supervised learning, so you have n IID samples, so each data point has an outcome assigned to it. So this is the data set that you have. You have n data points and each data point is a pair. So you have its example, observations, and you have its label or outcome assigned to it. That's what we have. Whether it's regression or classification, this is the same. Let's say I want to learn a linear function of features. So many a times what we have that all the x are my features. So these are my features. So these columns are my features that we have here. These are my examples. So when I'm actually in the original space, which is basically RD, I may have to resort to a non-linear classifier. But if I actually uplift my feature into a high dimensional feature space, my classification becomes linear. So that basically goes to the kernel properties. I can prove it later on in the question answer session, but I'll just believe in me. That if I uplift my features, if I map these features to a high dimensional space, then this high dimensional feature space, the classifier will be linear. So I can use this linear classifier. And this linear classifier is nothing but an inner product. That's where linear algebra comes. So theta is the parameter of my model that I want to estimate. That's an unknown. Phi of x is basically my features represented in a high dimensional space. So that's what we have here. So given any x, phi is known, and this is giving me the prediction, the outcome of this linear classifier. So that's what we have here. So you have a fully annotated, completely annotated data set, which I call as the training data, and I have a linear classifier. Now, how good is my model? So I need a cost function. That's where optimization theory comes in. So I want to have a loss that is saying that given an example xi, what is my linear classifier telling me? What should be the outcome of this xi? It is basically theta, this is inner product. Then I compare it with the true outcome. There is some loss assigned to it. And then I average it over all the examples. That's what I'm doing. So I'm actually going through, so I take the first row, input it to my linear classifier, I see what is my output. And then I compute the loss. How far away is this output from my true output? That's the discrepancy. And then I collect all the errors from all these examples and I average them. That's called the average or empirical loss. And what I want to minimize this loss. I want to find that parameter vector theta that minimizes this loss over the training sample. So that's the training loss that we have. So theta hat is my parameter that I want to estimate. If I know theta hat, I know everything about my classifier. So with this parameter vector, my classifier is completely determined. If I know this parameter vector, I know everything about the classifier. So what I want to have a model where theta hat is completely parameterizing my underlying model, which is basically here. That's what I want. So this is basically supervised learning. And where is the supervision coming? The supervision is coming through this interaction. There's always this comparison. My model thinks that this example should have this output, but I have the true output, so I can always have a comparison, and that comparison is fed through as a feedback kind of a loop in this model, and I can update my model, I can revise my model so that I'm constantly reducing my loss over the training samples. So that is a very simple three-way